Ramli, and my metric number is 224462. So today my friend and I will tell you about the second law of thermodynamics with heat engine. So some of you want to know what is second law of thermodynamics, right? Let me tell you. So what is second law of thermodynamics? Second law of thermodynamics said that the total entropy of an isolated system always increases over time, and energy naturally flows from areas of higher to lower concentration. Energy cannot be completely converted into useful work. Some of it will lose as heat. Basically, the second law of thermodynamics is all about how the energy moves and change in system over time. One of the major use of this law is direction of process. By using this law, it helps us to predict how and in what direction energy will flow. For an example, a hot cup of coffee cools down to the room temperature when energy moves out from the cup. Other than that, the second law of thermodynamics teaches us that energy has quality, not just quantity. For an example, the quality for car battery that have not used in a long time cannot be used. The energy is still there, but it has changed to the waste heat. As for theoretical limit for engineering system, the second law of thermodynamics being a major help to solve engineering system such as heat engine.
In thermodynamics, a thermal energy reservoir is an idealized body with specific characteristics that make it essential for studying energy transfer system. First, it has an enormous thermal energy capacity determined by its mass and specific heat. This allows a reservoir to store or release large amount of heat without undergoing any noticeable change in temperature. This constant temperature property make it a stable reference point for analyzing energy exchange process. In practice, thermal energy reservoirs are modeled after large natural systems. For example, ocean, lakes, and rivers act as reservoirs due to their vast ability to absorb and retain heat. Similarly, the atmosphere with its immense thermal capacity serves as another real-world example. These natural bodies are used to simplify thermodynamics model while maintaining practice relevance. Thermal reservoirs play a crucial role in systems like heat engines, refrigerators, and heat pumps. Heat engines, for instance, rely on high-temperature reservoirs to supply energy and low-temperature reservoirs to absorb waste heat, completing the cycle. Refrigerator and heat pumps depends on reservoir to transfer heat efficiency between space. In essence, thermal energy reservoirs are the backbone of theoretical and practical thermodynamics, offering the stability and frameworks needed to analyzing energy system effectively.
Heat engines. A heat engine is a device that converts thermal energy heat into mechanical work. It operates based on the principle of thermodynamics and typically involves the transfer of heat from a high temperature source to a lower temperature sink. The key feature of a heat engine is that it produces work by using the energy difference between the heat source and sink. Heat engine receive heat from a high temperature source. Heat engine take in energy as heat from sources like solar energy, oil furnaces, or nuclear reactors. This heat is the input energy for the engine to start its process. They convert part of this heat to work. A portion of the absorbed heat is transformed into useful mechanical work, such as turning a shaft or moving a piston. They reject the remaining waste heat to a low temperature sink. Not all the heat can be converted into work. The leftover heat is released to a cooler place like the air, water, or the ground. Heat engine operates on a cycle. The process repeats continuously in a cycle involving heat absorption, work conversion, and heat rejection, allowing the engine to function continuously. Now we move to thermal efficiency. What is thermal efficiency? Thermal efficiency is a measure of how effectively a heat engine converts the heat energy it absorbs into useful mechanical work. It is defined as the ratio of the work output to the heat input from the high temperature source. Maximum efficiency achieved when QC, which is heat rejected, is minimized, but due to second law of thermodynamics, no real engine can convert all heat into work. A perfect efficiency of 100% is impossible. Carnot efficiency, the maximum theoretical efficiency of a heat engine operating between two temperatures, TH and TC, which is high and low respectively. The efficiency is always less than 100% due to the second law of thermodynamics,
In a
which
steam power
states that
plant
some
example,
heat
the
must be
one on
rejected
here,
to the sink.
a critical component is the condenser, which you can see up there, where waste heat is rejected into the environment, typically rivers, lakes, or the atmosphere. This might raise the question, can we eliminate the condenser and save all that waste energy? Unfortunately, the answer is a firm no. As illustrated here, every heat engine must transfer some energy to a low temperature reservoir to complete the cycle. This is a fundamental principle of thermodynamics. Even under ideal conditions, it's impossible to convert all the heat into useful work. Without heat rejection process, the engine cycle simply cannot function. So while the rejection of heat might seem inefficient, it's an essential step in the operation of any heat engine. This highlights the importance of understanding and working within the constraints of thermodynamic laws when designing energy systems. So we have learned about heat engines, thermal efficiency, and the second law of thermodynamics. Now it's time to do some questions, and we're going to solve them together. So for the first question, it says a heat engine takes in 1000 joules of energy at 1000 Kelvin and exhausts 585 joules at 350 Kelvin. What are the actual and the maximum theoretical efficiencies of this heat engine? Let's find out. First, we figure out the actual efficiency by using the equation, which equates to work output divided by the heat input. Now we can derive the work output to be the work going in minus the work coming out, divided by the heat that we have put into the system. Now, if we take the values given in the question, the energy coming in is 1000 joules, and the energy going out is 585 joules. If we subtract and divide it by 1000, we get the actual efficiency to be 41.5%. So now hopefully you guys have learned about efficiency, thermal efficiency, Carnot principle, second law of thermodynamics, 1 minus temperature in the cold state divided by the temperature in the hot state. If we substitute the values given from the question, which are temperature from the hot state is 1000 Kelvin, temperature in the cold state is 350 Kelvin, we get our Carnot efficiency to be 65%, which is like approximately 25% deviation from our actual efficiency. So to summarize, a heat engine is a device that converts thermal energy into mechanical work while operating in a cycle. Key characteristics and principle of heat engines include operation. Heat engines receive heat from a high temperature source. Example, this could be solar energy, oil furnace, or a nuclear reactor. These high temperature source convert part of this heat into work, often in the form of a rotating shaft, and reject the remaining waste heat to a low temperature sink. Example, the atmosphere, rivers, or lakes. Secondly, we have a working fluid. A fluid is used within the engine to transfer heat while undergoing this cyclic process. Then we consider the thermal efficiency. This is a measure of the engine's performance, calculated as the ratio of the work output to the heat we have given as input. No heat engine can achieve 100% thermal efficiency due to the second law of thermodynamics. To state more about this second law of thermodynamics, or Kelvin Planck's statement, it is impossible for any cyclic device to convert all the heat it receives into work. This limitation applies both to idealized and actual engines. To give some examples, steam power plants are a common example where condensation are used to reject waste heat, completing the cycle. Removing the condenser is not feasible as it disrupts the cycle. The efficiency of a heat engine depends on the temperature difference between the heat source and the heat sink, as described by the Carnot principle.